Welcome to today's video on descriptive statistics. Measures that help to describe the data are classified under descriptive statistics. These include measures of central tendency, measures of dispersion, and skewness and kurtosis. Central tendency is a typical value of the entire data. The other figures congregate around this central tendency. It is usually located in the center or middle of a distribution. Measures of dispersion describe how the data are scattered or dispersed around a measure of central tendency. Measures of skewness and kurtosis help describe the shape of the frequency curve. The common measures of central tendency are arithmetic mean, median, and mode. Measures of dispersion are range, quartile deviation, standard deviation, mean deviation, etc. In life sciences, the most commonly used central tendency is the arithmetic mean, and the most commonly used measure of dispersion is standard deviation. So, we will focus on arithmetic mean and standard deviation. As we have seen in the previous video, data obtained from a sample or a population which has not been processed or modified is raw data. So we have raw data here, 8 observations, lengths of fishes in a fish tank. Arithmetic mean x bar is given as sigma x by n, where sigma x is the sum of all the variables and n is the total count or the total number of variables. So when we add all this, the total is 26.7 and we have 8 observations. So the mean is 26.7 by 8, which is 3.34. Standard deviation for raw data is given by the formula sigma, which is standard deviation, is equal to root of summation of x minus x bar the whole square by n, where n is the sample size, so the total count. For a sample size less than 10, n minus 1 may be substituted instead of n. And as we know, x stands for the variables and x bar stands for the mean. So we have the same set of values here which we saw for mean. And now if we need x minus x bar, we have to calculate the mean which we have calculated in the previous slide. It is 3.34. The next step is to find out the difference between each x value from the mean. So 2.5 minus 3.34, which is minus 0.84, 3.4 minus 3.34, which is 0.06. So the difference of all the x values from the mean are calculated and tabulated. Next, we need the square of this in the formula. So this difference between x and the mean is squared and we get the values here. The total is 2.739 and this is what we need for the numerator. So it is 2.74 and we have 8 observations. It is less than 10, so 8 minus 1, 7. So we get the standard deviation as 0.625. Whenever we present our data in a table, we present it as mean plus or minus ST. Even representations in diagrams or graphs, we represent it as 3.34 plus or minus 0.63 here, which is mean plus or minus ST. Just for the sake of comparison, we have another set of data, which is the length of fishes in another fish tank. And here also we have given the mean plus or minus ST. Representing the data in terms of central tendency and dispersion helps us to draw conclusions easily. Other terms associated with standard deviation are variance, which is the square of standard deviation, standard error, which is standard deviation by root n. In some cases, in tables, it is represented as mean plus or minus standard error. And coefficient of variation, which helps us to compare two sets of data, which is standard deviation by mean into 100. Before we move on to measures of skewness and kurtosis, let us understand the features of a normal distribution curve. If the frequency curve of a data resembles a bell-shaped curve and it is symmetrical on both sides of the mean, here the mean is represented by mu, then we can decide that the data is normally distributed. So if it is a perfectly normal distribution, the mean, median and mode will coincide and it will be represented in the peak of the curve. This is the peak and these are the tails of this curve. Median is a point which will divide the data into two equal halves when you arrange it in an ascending or descending order, and mode is the data value which occurs the maximum number of times. All the three coincide in a perfectly normal distribution. The tails are asymptotic and the main feature is 68% of our data values will fall between mean plus or minus standard deviation, and a total of 95% of the data values will fall between mean plus or minus 2 times the standard deviation, and 99% of the data values will fall between mu plus or minus 3 times the standard deviation. For example, suppose the mean is 10 and the standard deviation is 1, then 68% of the values will fall between 10 plus or minus 1, that means between 9 and 11. 95% will fall between 10 plus or minus 2, that means it will fall between 8 and 12. And 99% will fall between 10 plus or minus 3. So this is a feature which we will observe in a normal distribution curve. There are many tests which will help us to know if our data is normally distributed. Some statistical tests are Anderson-Darling test, and plots are histograms, Q plots, box plots, etc. But a measure of the mean, median and mode to see if they coincide and to see how the data is dispersed when we know the mean and standard deviation, and measures of skewness and kurtosis can help us to understand approximately the type of distribution of our data. Most of the biological measurements follow a normal distribution curve. So skewness will describe the extent of asymmetry in a distribution. As we saw here, in a perfectly normal distribution, the mean, median and mode coincide. Whereas when the data is positively skewed, we have an asymmetry here. The right side tail is longer. And when the distribution is negatively skewed, we have a tail in the front. And the mean, median, mode do not coincide. They are usually represented by the relationship mode is equal to 3 median minus 2 mean. There are many measures of skewness. Karl Pearson's coefficient of skewness is given by the formula mean minus mode by standard deviation. And as we know, for a perfectly normal distribution, the coefficient of skewness will be 0 because mean, median, mode are same. A value of +1 to -1 is acceptable for considering a data to be normally distributed. If there is more than one mode or mode is ill-defined, the formula used may be 3 into mean minus median by standard deviation. Kurtosis will help us to understand how the data is distributed between the peak and the tails of the distribution. Or we can tell that it defines how heavily the tails differ from the tail of a normal distribution. So if you see here, the red colored curve is the normal curve referred to as mesokurtic. A leptokurtic has a sharper peak and heavier tails, which is represented by black. And a platykurtic curve is represented by green, where the peak is broad and the tails are comparatively light. Measure of kurtosis given by Carl Pearson's formula is mu4 by mu2 square, where mu refers to the moment, and the moment is calculated using the formula 1 by n into sigma x minus x bar. It is evident, like we did it in the case of standard deviation, the same procedure we have to follow here. We have to find out the mean of the data and see the difference between each data value from the mean, and you have to find the summation. This is divided by the total count to get the first moment. If you square this term, then it is the second moment. If it is cubed and you find out the sum, it is the third moment. And if it is to the power 4 and then we find out the sum, it is the fourth moment. So here it is the fourth moment by the second moment square. For a mesokurtic curve, kurtosis value is 3. For a leptokurtic curve, it is greater than 3, and for a platykurtic curve, it is less than 3. Plus or minus 1 deviation is allowed for a data to be considered as normally distributed. And if in a software this 3 is optimized to give a result as 0, then plus or minus 1 kurtosis is permissible for normal distribution. So as we have seen here, there are standard tests to see if our data is normally distributed. You have statistical tests and plots, but measures of descriptive statistics also help us to get an idea about the nature of our data. We have seen the calculations and the formula required. All these calculations can be done using the insert function of fx, but each of these tests has to be done independently. Each test has to be carried out separately. Whereas if we use the data analysis pack, this single test you will get all the measures of descriptive statistics. So I have a set of raw data here, and if I use the data analysis pack, I get the full summary statistics. I get the measures of central tendency, mean, median and mode. We get the measures of dispersion, standard deviation, standard error and variance. We get measure of kurtosis and skewness, range, which is the highest value minus the least value. We get the minimum value, maximum value, what is the total sum, as well as the number of observations. So this is the advantage of using data analysis pack for calculation of measures of descriptive statistics. In the upcoming videos, we will see the measures or tests which we can use under inferential statistics. Thank you.